Okay, let's start dealing with the stuff in today's session, friends. Today, specifically, we would be talking about vertical circular motion, a circular motion in vertical plane. Earlier, mostly what we have seen is, circular motion in horizontal plane. So there, the motion could have been uniform or non-uniform depending upon the circumstances. But when I'm talking about vertical circular motion, specifically one needs to understand that it cannot be uniform. Now we are getting into the reason why that's going to happen. So let's just concentrate on the animation over here. Say for example, a body is performing vertical circular motion in this manner you can see. Right. So let's talk about different positions of this body at different intervals of time. Okay, just give me a moment. Yeah. So you can see the body can be at times, at the topmost point. So at the topmost point, obviously the weight which would be acting on it would be mg and it would be in the downward direction. Let's talk about another position of a body where you can see the body is at midway position. So you can see the second position, midway position. Let's talk about the bottommost position. So, and let's talk about the fourth position which is being seen over there. So everywhere if you observe friends, the distance of the object from the center of earth will vary. Accordingly, the value of acceleration due to gravity will also comparatively vary, and that will impart acceleration to this type of motion, and therefore we can say the vertical circle cannot be a uniform motion basically. So this is the basic understanding behind it. Before we move ahead towards the further analysis, please make a note of this and then we move forward. Okay, hopefully things are sorted out. Let's move ahead. Let's talk about what vertical circular motion is. Okay, so when a body moves in a circle in a vertical plane, we will call that motion of the body as vertical circular motion. And to be more specific, we need to derive equation for tension and velocity at different positions of vertical circular motion. So I have mentioned which positions we were talking about. Specifically, we will talk about the topmost position as shown in the previous slide, then the bottommost position, and the third one would be the midway position. So these are the specific positions where we would establish equations for tension and velocity specifically. So for that, let's consider a body of mass m tied to a string and whirled in a vertical circle, say of radius r. So here is the case. So let's divide it into two parts, basically 4 quadrants you can see. Let O be the center of the circular motion, R is the radius, H would represent the highest point you can see, M stands for the midway point you can see over here in this diagram, H stands for highest point, M stands for the midway point, and L will stand for the lowest point over here. So let's position it. So at the highest point you can see the weight would be acting. You can check out the arrow over here. It would be acting towards the center. Okay. So the weight will be acting towards the center and the tension in the string will also act towards the center basically. So therefore TH is shown towards the center in this case. Let's talk about the midway position. You can see this is how the direction of the tension would be at the midway position in the string. Lowest point, if we talk about, this is the direction of the tension in the string at the lowest point. So we are supposed to establish equations for this. Let's move ahead then. So before taking a specific position anywhere, what we can do is, instead of taking a specific position, let's talk about the general position first, and then we try to specify it. Okay. In, in this case, okay. So let's talk about a general position, friends. Yeah. Yeah. Let's talk about a position P. You can see it on the screen, basically. Right. So at position P, if you observe, you can see the forces which would be acting on at position P would be, the weight vertically downwards. So you can see at position P, the weight acts vertically downwards. This is the direction of the tension in the string at position P. So say it makes angle theta at the center, you can see. So let T be the tension at position P in the string. So obviously, if that angle is theta, then we can work out the geometry, and there onwards, you can resolve mg into two components. The adjacent component will be mg cos theta, and the perpendicular component will be mg sin theta, friends. All right. So here in this case, you can prepare a vector diagram over there for applying law of parallelogram, and you can resolve the two vectors. Mg being resolved into two components, mg cos theta and mg sin theta. Okay, just give me a moment. Okay, so here in this case, if you observe at point P specifically, if this angle was theta, obviously these two lines are parallel lines, and this angle will also be theta as per geometry, and that's how the resolution has taken place. So we are analyzing a general point P in vertical circular motion, and then once we get equations for that, we will try applying the same for the specific positions. When I say specific positions, the specific positions are the highest position, the midway position, and the lowest position, friends. So before we move ahead, I want you to quickly note down this diagram where the forces are being resolved, and you come across the force diagram for a position P where we are trying to analyze vertical circular motion, friends. Okay, hopefully I've noted this down. Let's move ahead then. Okay, so we are talking about the same diagram. The same diagram is being mentioned here on this slide also. We have discussed the same diagram. We have talked about the forces like weight, tension in the string, weight being resolved into two components, m cos theta, mg cos theta and mg sin theta. Can see. So then let's talk about what can be the net force towards the center of the circle at position P. So if we talk about position P, the net force towards the center will be the difference between T and mg cos theta. Because they are acting opposite to each other, the resultant force which would be directed towards the center of the circle would be given by T minus mg cos theta, friends. This would be the net force acting towards the center of the circle. Okay. Yeah. Now this force will provide the necessary centripetal force which is required for the vertical circular motion of the body. So whatever is the resultant force at point P, so we have established at point P, the resultant force will be T minus mg cos theta, and that resultant force would act like centripetal force for the circular motion. So I can equate T minus mg cos theta to the centripetal force. Okay. Before we equate that, you can quickly note down this slide so that we move ahead, friends. Okay, hopefully you have made a note of this. So let's move ahead. Again, what I was trying to say, I'll just recall that point for you people. The resultant force which is acting along this line is T minus mg cos theta as per the diagram. and that force has to be equated to the centripetal force, because that will provide the resultant force, will provide the necessary centripetal force required for the circular motion. So let's move ahead and let's equate the, so I can say T minus mg cos theta to be equated to centripetal force, and that is mv square by r. So this is the basic equation which will be governing the phenomena. If I shuffle it in terms of the tension capital T, the equation then becomes mv square by r plus mg cos theta. So this is the equation for tension at any general point P. So we can see we have derived the equation for tension at any general point P, and now we will try to work out tensions at the specific points. So out of those specific points, the first point which we are considering over here is the highest point B. Now if you observe the previous diagram, what is the value of theta if you talk about P? Okay, highest point. So look here, concentrate. Now what can be this angle theta if you move to highest point, friends? Okay, so when you move to highest point, this theta will be 180. So here also what we are doing, we are substituting the value of theta as 180 at the top. So when you substitute the value of theta as 180, the equation at the highest point for the tension would become TH equal to mv square by r plus mg cos. Instead of theta, I am substituting it as 180, and we all know what's the value of 1 cos 180? It's minus 1. Therefore, then this equation will further become mv square by r minus mg, because here cos 180 is minus 1. So you can see at the top, the tension in the string is minimum. Always remember why, because there is a subtraction taking place. Okay, because of this angle, you can see the total tension at the highest point would be the difference between these two. Therefore, it is minimum at the top. So in order, important statement to make over here is, in order to continue circular motion, the minimum tension must be equal to 0. Why minimum tension must be equal to 0? Again, I am showing you the same diagram, and let's have a look at it. See, if the tension is not 0 at the highest point, what it means? The object at the highest point will come down because of this tension. If it is not 0. If the object comes down, the string won't be taut. Taut means tight in a way, and it will hamper the vertical circular motion. Or in simple words, the particle won't be in a position to perform vertical circular motion. Other way of understanding it is, if the vertical circular motion is being performed, then it is an indication that this TH must have been 0. Now, if I put TH equal to 0 for the string to be in a tight position or a taut position, you can say, then I'll have to put this TH equal to 0. Fine, friends. And then I'll have to see how the equation works out to be. So before, so TH, I'm going to put it as 0. So here at the highest point, you can see this is the horizontal velocity at the highest point, mv square by r and th. Okay, so you can just put this th as 0. I have given you the reason why we are putting th as 0. When you do that, what changes occur in the equation, that's what we want to see. But then before we move ahead towards that slide, you please make a note of this quickly. Okay, hopefully you have noted it down. Now what I'm going to do, I'll put th as 0 in this equation, and when I put it th as 0, the v changes to vh. Why vh? Because we are talking about velocity at the highest point then. And then the difference between the two is equal to 0. Shuffle the values. So mv square h as a suffix by r equal to mg. M will get cancelled from both the sides. So v square at the highest point is rg. So at the highest point in vertical circular motion, the velocity or the speed would be root rg, friends. So important point to be noted. Okay, so you can see, therefore the body must reach at the highest point h with minimum speed root rg in order to remain in circular path. Because other way of understanding it is, if this speed is not maintained, then the string will slacken and the body won't be able to perform circular motion, vertical circular motion to be more specific. Okay, so this is how we have worked out tension and velocity at the highest point. Now let's talk about the lowest point. So if you try to recall the diagram, at the lowest point the value of theta would be 0. So if that is the case, then our equation TL will be equal to, here you are supposed to make that correction, TL is equal to, okay, mv square by r plus mg then in this case. So because cos 0 is 1, it is plus 1, so it won't be a negative sign over here. Here it has to be equal to sign, okay. So TL equal to mv square by r plus mg. So you have to make that correction, friends. Okay. Then the tension would be, there is no reduction between the two forces. In fact, there is addition between the two forces. So obviously the tension will be maximum at the bottom. So whenever it comes to circular motion, specifically vertical circular motion, you should understand one thing, that at the top the tension would be minimum, that is 0, whereas at the bottom the tension will be maximum. And you can see, if the object comes to the bottom, just have a look at the diagram. From the top, if it comes down to bottom, here the tension at the lowest point will increase. It will be, you can see, mv square by r plus mg in this case. It's going to increase, so it will be maximum at the bottom. So before we move ahead towards the next part of the analysis, make a note of this quickly. Here the only correction would be equal to sign, TL equal to. Okay, hopefully things are pretty clear till here. So let's move ahead then. We got, at the lowest point the tension will be mv square by r plus mg. Remember that. Let's move further. What can we say about the potential energy at the bottom? It will be minimum. Okay. Change in potential energy when the body moves from bottom to the top will be mg into 2r, you can see. When the body, if we consider this as reference, okay, and say from center to bottom the distance is r, center to top the distance is r. At the bottom it is moving with some velocity at the bottom, say vl, and at the top it is moving with some velocity, say vh, which we have calculated as root rg. Now we are interested in finding out the velocity at the bottom, so we are using law of conservation of energy. So what we can say, whatever was the energy at the highest point, the same energy will remain conserved at the lowest point, but there will be some changes in kinetic and potential energies. So we are going to make use of law of conservation of energy to derive the equation for velocity at the bottom of the vertical circle. At the top, we have already derived it, and that equation was Vh is equal to root Rg, if you remember previous slide. So let's talk about law of conservation of energy. So between the highest point and the lowest point, if I consider lowest point as a reference, then the height is r and r, that is 2r. You can see that potential energy will be mg into height, that is 2r. So by law of conservation of energy, can I say kinetic energy at the lowest point plus potential energy at the lowest point will be equal to kinetic energy at the highest point plus potential energy at the highest point. So this is the equation where I am comparing 2 points, lowest and highest point, with the help of law of conservation of energy. Now I'll be putting the values in these equations correspondingly, and let's see how we put the values. So please have a look at it. Be careful about what we are doing here. So kinetic energy at the lowest point, I can write it as half mv square with L as a suffix because I'm talking about the lowest point. What can you say about the potential energy at the bottom? Obviously, R and R becomes 0. So 2R is 0 over here. So here you can see it is 0 potential energy at the lowest point. Let's talk about kinetic energy at the highest point. Can I say kinetic energy at the highest point is half mv square with H as the suffix? What about the potential energy at the highest point? Can I say it is mg into height, that is 2r? So now I have all these equations. I have the value for Vh also. And the value for Vh was root Rg. So if I square it, so if I square the value of Vh and I put it over here, and let's see how the equation works out after squaring and substituting it over here. So the equation then becomes half mv square for the lowest point equal to mg2r, you can see mg2r plus half m, and instead of vh square it is rg over here. Just square it and substitute it. So shuffle everything now. M can get cancelled. You can take m common. Just shuffle it first of all. When you shuffle it, you will get VL square will be equal to take the LCM. It is like 4RG plus RG. So ultimately it will be 5RG. So velocity at the bottom ultimately will be given by, yes, root 5RG. So if you observe, at the top, the velocity was root RG. Whereas at the bottom, the velocity is root 5RG. It has increased. So it has to increase to this level when the object moves from top to bottom, so that the particle is able to perform vertical circular motion. So you can see, we can make this statement then, this is the minimum speed required at the bottom to maintain circular path when it comes to vertical circular motion, friends. So please make a note of this before we move ahead. Then there is another point, say midway point, to be analyzed. We need to think about what would be the velocity here also at midway. Okay, so again we will use law of conservation of energy there also. But before we do that, I want you people to quickly note this down. Okay, hopefully I've noted this down, friends. Let's move ahead then. Yeah, add the horizontal distance. Okay, just a minute. Yeah, wait. Okay, no problem. Just give me a moment. Yeah, please make a note of it and let me know so that then we move ahead. Okay, Akansha, I got your message. Chalo. Let's move ahead then. So the next point of discussion is, from the bottom point, if we move to the midway point, then what would be the velocity? So now it's very clear that at the highest point, the velocity will be root rg. At the lowest point, the velocity will be root 5rg. Now we need to understand what would be the velocity at the midway position in vertical circular motion. So here you can see the velocities are changing. Had it been horizontal motion, circular motion, the velocity simply would have been root rg everywhere. But here the velocity is changing because the acceleration due to gravity correspondingly varies from point to point. Therefore, there is variation in the equations of velocities also, friends. So hopefully this is done. Let's move ahead. So at the midway position, if you observe this diagram, you can see at the midway position angle is 90, theta is 90, and you all know cos 90 in this case will be 0. Okay, but then when body moves from bottom to the midway position, what will happen? Here the potential energy was 0. Whatever energy was kinetic energy. So kinetic energy will get converted into potential energy at the midway position. So what will be the total energy? If I compare the total energy at the bottommost position it will be half mvl square plus potential energy was 0. So this is the equation for total energy at the bottom. Similarly, this can be the equation for total energy at the midway position, where potential energy won't be 0. Why? Because at least the object is moving up by height r, you can see, and therefore potential energy will exist. So let's put total energy as half mvm square, which we don't know, plus the potential energy we can estimate mg into height. What is the height by which the object has been raised? R. So this R comes in picture over here. But as per law of conservation of energy, whatever is the total energy at the bottom should be equal to the total energy at the midway position. So we can equate this. Okay. So when we equate this again by law of conservation of energy, you can see kinetic energy at the lowest point L plus potential energy at the lowest point L will be equal to kinetic energy at the midway point plus potential energy at the midway point. Let's substitute the values. So you can see you are equating these two equations. Shuffle everything. You know, we all know VL is equal to root 5 RG. Just now we have derived. Here instead of H, it should be M. Okay, it's wrongly mentioned. This M. See, here it was M, you can see. The same thing has to be continued over here. It's a typological error. So place it as M over there. Okay, let's move ahead. So minimum velocity at the bottom, we all know, is root 5 rg. So we can substitute VL as root 5 rg, square it and put it in this equation. You can substitute it as 5 rg over here. Alright, so just substitute it and let's see. So half m 5 rg will be equal to half m, again it's a typological error over here. Instead of h, it should be m. Okay, midway position, suffix should be m plus mgr. So let's solve it. So you take mgr on this side, so it will be 5 by 2 mrg minus mrg. Take the LCM. So when you take the LCM and compare, you will get v square for the midway position is 3rg. So the speed at the midway will be root of 3rg. So we got the speed, value of speed for the object performing vertical circular motion at the midway position, and what amount it is? Root 3rg. So at the top it is root rg, at the bottom it is root 5rg, and at the midway it is root 3rg. Same thing would be applicable here also, it will be root 3rg. Please make a note of this slide basically so that we move ahead, friends. So you can say this is the minimum speed required at the horizontal diameter to maintain circular path. Obviously, we are talking about vertical circular motion over here. So hopefully things are pretty clear till here. So let's move ahead then. If you are done with it. Okay, so I assume you are done with it. Let's move ahead. Fine. Now here comes equation for velocity at different positions of vertical circular motion. Those were specific positions. At the top it was root rg, at the bottom it was root 5 rg, midway it was root 3 rg. So you talk about the reference figure, you can see if this is the reference line, and these are the positions. H stands for the highest position, L stands for the lowest, and M stands for the midway position. This is how the directions of the velocities at the corresponding positions would be. You just drop a tangent, okay, and you come to know the directions of velocities. So let's talk about a general position P. So at P, if I want velocity, so P is a point which is not any specific point. Neither it is the highest point nor it is the lowest one, or you cannot call it as the midway point also. It's a general point P. Here if I want the velocity, then what would the equation look like? So let's draw, let's connect P to the center and let R be the radius. So obviously you can check out this angle theta. So let's have a geometrical work over here done. So please concentrate. Say example, if this is R, okay, and this entire thing is again R, and if this height is H, then the remaining height will be R minus H. So this is how we work out geometry over here. Now if this is done and you all agree to this geometry, then if you talk about this triangle OPD or ODP in this case, it's a right angle triangle, and cos theta in this case will be given as, you can see, adjacent side upon hypotenuse. So that is R minus H upon R. So shuffle it and you get R cos theta equal to R minus H. You take R over here on this side. So from this, we shuffle everything in terms of H. H will be R minus cos theta. So here R minus R, sorry, it won't be R minus cos theta. It will be R minus R cos theta. This R is missing over here. Then you take R as common, and what remains in the bracket is 1 minus cos theta, friends. You got this height. Which height? This particular height, H. And that the value of that height is R1 minus cos theta. So now if I know the height, I can equate the potential energies there. So before we move ahead, please make a note of this very important slide. Okay, hopefully you have noted this down. So let's move ahead, friends. So according to the principle of conservation of energy, again let's get back to this. Okay, whatever was the total energy at the lowest point should be equal to the total energy at point P. So that's what total energy principle says. So total energy at the lowest point L will be the total energy at point P. So again we place the equation in the similar format. Kinetic energy at the lowest point plus potential energy at the lowest point will be equal to kinetic energy at point P, which is the general point, plus potential energy at point P. Let's put the values over here. So for kinetic energy at the lowest point, I can place it as half mv square L plus potential energy at lowest point is 0, equated to half m v square P. P stands for any general point, plus mgh. Now this h we have worked out. Just now we have worked out the value. What was h? H is not 2 mgr here in this case. I'm sorry, it's wrongly mentioned over here. It will not be 2r. Okay. Yeah. So should not have been 2r actually. Let's see what value h. It should be in terms of h basically. Okay. Yes. Okay. So from this you can work out the value. Okay. So what you can say is, mvp square. Okay. The potential energy is say 2 mg h. Instead of r, it will be h basically. Okay. So not 2r, but then h over here, which has been taken into consideration here. तो इधर आप लोग क्या कर सकते हो, h को h ही रखो फिलहाल, and then when you simplify it, you get v square for the lowest point will be equal to, v square for the general point basically. Okay, so ultimately at the general point you can get this value as root of, if you shuffle this, vp will be root of, here it should be vl square, and here it should be, instead of plus, it should be minus basically. Just check out this one. So let's move ahead. But what is the value of h? H is, you can see, 1 minus r into 1 minus cos theta. This is what we have worked out. So we will put the value of h over here. So here they have corrected it. Okay, here the mistake was a negative sign to be mentioned, and instead of p it should have been l. So here instead of p it should have been l, minus sign is worked out, 2g, and instead of h it should have been r 1 minus cos theta. So h has to be substituted as r 1 minus cos theta. So here also instead of h you will substitute it as r 1 minus cos theta. So here the typological error in this step was a negative sign. Here the suffix should have been L. Here instead of h it should be r after substitution. This is the general formula for velocity at any point, you can see. With those corrections, friends, please see to it that you make those corrections which I have said. Again, I repeat the corrections in this slide. Here it should have been, okay, minus sign. Here the suffix should have been L for the lowest point. And once you substitute h as r1 minus cos theta, so here instead of h it should have been r. That's the only correction which you have to make. Okay. Hopefully you make those typological corrections, errors being corrected. So let's move ahead once you note it down, okay, with those corrections. So this is the value of speed at any point for vertical circular motion, friends. Hopefully things are noted down. Let's move ahead. Let's discuss the conservation of energy in vertical circular motion. So we can see potential energy of the body in vertical circular motion is measured with the reference to the bottom position. So at the bottom position, you will consider the height as 0 and potential energy as 0. So that's the reference position, lowest position. So when the body in the vertical circular motion is at bottom, we all know the speed is root 5 rg. Potential energy is 0. So what can be total energy? Potential energy plus kinetic energy. So kinetic energy can be worked out as half mvl square. Put the value of VL as root 5 rg, square it. So kinetic energy will be 5 by 2. When you substitute it, okay, I should have substituted it. When you substitute this, then only this 5 term will come. Okay, there has to be some correction. Yeah, 5 by 2. Okay, so let's say when you put it, okay, so here you are supposed to put 5 rg. So kinetic energy will be 5 by 2 mrg. So instead of v square l, it should be rg over here. So this plus 0 will give you 5 by 2 mrg, friends. So the total energy in this way at the bottom can be worked out as 5 by 2 mrg. The correction is instead of v2 square l, either rg hona chahiye. That's the only correction. So I got the equation for total energy at the bottom. And what's the value? 5 by 2 mrg. Please make a note of this. Again, I will work out the total energy at top. Then I can work out total energy at a midway position. And then we will see whether these total energies are same everywhere. Hopefully you have noted this down. Let's move ahead then. Yeah, at the top, that is the highest point. We know the speed there is root rg. So potential energy at the top will be mgh. H is 2r in that case. So potential energy will be mg into 2r. You can see. Then kinetic energy can be worked out as half mvh square. But vh is root rg. So square it and substitute it over here. So kinetic energy will be given as, you can see, half mvh square. So put the value of total energy, potential plus kinetic. So when you add this potential 2 mgr plus half mgr, you take it as 2 mgr plus half mgr, and you get this as, 5 by 2 mgr or mrg. So you can see at the highest point also the total energy comes out to be 5 by 2 mgr or mrg. At the lowest point the total energy was 5 by 2 mgr. So please make a note of this and then we move ahead. Let's work out some midway position. So what are these 2 points suggesting us? So whether it be lowest position or highest position, the total energy has to remain constant in vertical circular motion. So that gives us a proof of law of conservation of energy in vertical circular motion, friends. So here you can see, can make a statement, total energy in vertical circular motion is conserved. So other way of understanding it is, when the body moves from bottom to the top, you can say kinetic energy will get converted into potential energy. Whereas when it moves from top to bottom, the potential energy gets converted into kinetic energy. Just like in SHM, if you have seen, the similar type of conservation takes place over here also. Please make a note of this, friends. So in boards or in exams, if they ask you to prove that the total energy is conserved in vertical circular motion, this is the way to go about it. Okay, hopefully things are clear till here. So let's move ahead then, friends. Okay. One more interesting aspect, whichever were the kinematical equations in a translational motion, analogous equations would be used in circular motion or rotational motion. So if you all remember, for linear motion, we have derived kinematical equations like, there were three equations of motion. First one was V equal to U plus AT, where V stands for linear final velocity, U stands for linear initial velocity, A stands for linear acceleration. Second equation was S is equal to ut plus half at square, where S stands for linear displacement, friends. And the third equation was V square equal to U square plus 2AS, where you all know S stands for linear displacement. You all know what V and U means, okay? In the similar terms, you can see it's been mentioned. Similar terms, similarly for circular motion or rotational motion also, which we are going to study in the subsequent stages, the three equations can be converted in this angular format. So here you can see, instead of V equal to U plus AT, you can put it as omega equal to omega naught. This naught has to be suffix. Wrongly it has been mentioned. So omega will be the final angular velocity. Omega naught will be initial angular velocity. Plus, instead of A, it is alpha. Instead of linear acceleration, it will be angular acceleration over here, alpha, and T remains as it. This is the first kinematical equation for circular motion or rotational motion. Second equation can be, here you have to make a correction, okay? So it's not zero, it's omega naught, it's a suffix. Okay, the second equation, or third equation directly you can come to, omega square will be equal to omega naught square plus 2 alpha theta. The same thing is being mentioned. The linear terms are being converted into angular terms. Okay. Now if you compare it with the second equation also, you can see S is being converted into theta. Linear displacement is converted into angular displacement, friends. So U stands for omega naught into T. So again, you have to make that correction over here. Omega naught into T. O is suffix. Okay, and half, instead of A, it has to be alpha T square, and so on. So whatever were the equations here for linear motion, now we have these equations for angular motion, friends. So here onwards, we will start applying the set of equations for circular or rotational motion as well. So here the corrections are to be made. Omega naught, 0 is the suffix over here. Here also 0 is the suffix. What omega naught indicates? Initial angular velocity. Omega indicates final angular velocity. Theta is angular displacement. Alpha is constant angular acceleration, friends. So please make a note of this slide. Okay. Hopefully you have noted it down. Okay. So here comes the question for you people. At what angular speed should the earth rotate about its axis so that the apparent weight of a body on the equator will be 0? And what would be the length of the day at that time? So radius of Earth is given to you as 6400 kilometer, and acceleration due to gravity is 9.8 meter per second square, friends. So what they are expecting here, with what angular speed will the Earth rotate? So radius given 6400. Yes, Yashraj, you can unmute and speak. You have any doubt? Yashraj, you can unmute and speak.
So can you show the previous slide?
Yeah, definitely, definitely. Okay, I'll just show the previous slide to Yashraj and then we will come back to this. Okay. Yeah. So once you are done with it, Yashraj, let us know. We can move ahead then.
Yes, sir. Done. Thank you, sir.
Okay, no problem. Thank you. So let's come back to this question, friends. Here we are talking about angular speed with which the Earth should rotate so that the apparent weights on the of the body on equator will become zero, and then the length of the day at that time. So when the radius is given converted into meter, they are expecting omega and t. So when can the apparent weight of the body on equator become zero? When the centrifugal force mr omega square would be equal to mg. So when this force will nullify the weight, then people on the earth will start feeling weightless. Okay, it's a case of weightlessness. The mm will get cancelled from both the sides. So omega would be given by g by r. If you observe, so omega will be root g by r. Okay, it's not g by r. It is omega is root of g by r. Okay, so make that correction. Yeah, here in solution they have mentioned it clearly. So omega would be worked out as root of g by r. We know g, we know r. We can substitute the values. And once we substitute the value, friends, you get the equation. You get the value, sorry, root 9.8 divided by 64 into 10 raised to minus 6. So when you solve it, you will get omega. And then once you get omega, you can get a new time period then, length of the day that time. So generally, normally the length of the day is 24 hours. Let's see what would be the length of the day if Earth starts moving with this angular speed. So before I show you the next slide, before I discuss the answer with you people, please make a note of this. Okay, fine. Hopefully you are done with it. So when you solve this, there are log table calculations also mentioned so that you can cross verify these calculations when you work it out at home actually. Okay, can make a note of this log table calculations as well. Okay, hopefully things are sorted out. Here again you come across these log table calculations, and when you solve it, the final value for the omega will be 1.237 into 10 raised to minus 3 radian per second. What does that mean? If Earth starts moving with this angular speed, then the people on the Earth will start feeling weightless, basically. So time period, corresponding time period, we can work it out as 2 pi by omega. We can substitute this value of omega over here. When you substitute it, and when you try solving it for time period, again log table calculations are also mentioned for time period, you can see. So that time comes out to be 5058 seconds. So Earth should rotate with this much speed, and then the length of the day would be 5058 seconds. So just divide it by 60, you will get the minutes. Divided by 60, you get hours. Then you will see how the length of the day decreases, you can see. Fine. So please make a note of this before we move ahead towards the next question based on vertical circular motion which we have studied. Okay, hopefully you have noted this down. So let's move ahead then. Yeah, here comes an interesting question. In your textbooks also they have mentioned this. A motorcyclist riding in a vertical circle, hollow sphere, or we also call it as a death sphere. Normally, it happens, you know, during circus and all this stuff. So what is happening is you are supposed to find he is moving. The motorcyclist is moving in vertical circle in hollow sphere of radius 5 meter. You are supposed to find the minimum angular speed required so that he does not lose contact with the sphere at the highest point. At the highest point, why he is going to fall down? Because of its weight. So if the centrifugal force balances his weight, then what will happen? He won't fall down. If that balancing does not take place, then he will fall down. So at the highest point, the motorcyclist will not lose contact only when this force nullifies the weight. Mr omega square equal to mg. So that's the speed with which he has to move so that he does not lose contact at the topmost point and fall down. Alright, so m will get cancelled here, and ultimately you will get omega as root g by r. So it is root 9.8 by 5. When you solve it, it will be 7 by 5. That is 1.5 or 1.4 radian per second, you can see. So yeah, this motorcyclist will have to move with a speed of 1.4 radian per second so that he is not losing contact at the topmost point, and you know he is successful in his attempt. Please make a note of it basically.